Hi, everybody. All right, for this video, we're going to try to work through these guided notes um, and come up with a relationship between integrals and derivatives. We're really close to understanding the fundamental theorem of calculus. And so I'm hoping that this sequence of exercises will help us make some connections, and hopefully it'll feel a little bit like discovery. So if you want to work ahead on me on this, feel free to do that. I'm going to try to work so that I'm not wasting your time. Um, let's go ahead and start things off with, all right, we're supposed to draw this line, y equals 2t plus 1, and then use geometry to find the area under this line above the t-axis and between the vertical lines t equals 1 and t equals 3. So yeah, we're finding the area of a trapezoid. If we're doing 2t plus 1, it means we would have a y-intercept there. We would go through the point 1, 3. We would go through the point 5, 2, or 2, 5, and we would go through the point 3, 7. So if I connect those dots with the line, yeah, that's our line, y equals 2t plus 1. Um, And yeah, we could go vertical lines here and here. We're trying to find the area of that trapezoid. And yeah, we could totally do that. Area equals 1/2 of, the sum of the bases. It's the average of the bases times the height. And in this case, you know, uh, this part is the height, and these two sides are the bases. So we could find the lengths of these and then do all that math. So the length of the one here at 1, that's of length 3. The height here, that's 2. And then the other base here goes from 0 all the way up to 7. So that's of length 7. So yeah, if we do the area equals 1/2 3 plus 7 times 2. The idea is that we get 10 out of this. So the area of that trapezoid should be 10. That's a good start. So we found the area of one trapezoid, and now we are going to be interested in making this a little bit more general. So now we're going to let x values come in, and we're only going to allow x values that are greater than or equal to 1. A of x is going to be the area of the region that lies under the line and between t equals 1 and t equals x. So let's sketch this region. It's going to look very similar to what we did up above, except this time the right-hand endpoint is going to be, some value x that we're allowed to slide. We're allowed to make it any number, just so long as that number is greater than or equal to 1. And so let's try to make this happen again. We'll draw this line. Um, I did this so that, yeah, we're kind of running off the page a little bit. We're all right. Okay, so we're still calculating the area of this trapezoid. Um, but yeah, that's t equals 1. So this is still 3. This is x. And so the height of that will be 2 times x plus 1 because, it goes up to the function y equals 2t plus 1. So that length will be whatever the x value is, times 2 plus 1. And yeah, could we find, again, I guess, we didn't do the bottom. The bottom height should be, well, that's the difference between x and 1. So it's x minus 1 is that distance. Here, if we start a of x, it'll be 1/2 times the sum of the bases, so 3 plus 2x plus 1 times the height. The height is x minus 1. Okay, and let's see if we can reduce this a little bit and make it better. This is going to be 1/2 2x plus 4, x minus 1, okay. And so this, will turn out to be x plus 2 times x minus 1. And that's pretty good. We could also multiply this out so that we get x squared, 2x minus 1x gives us a plus x, and then a minus 2 at the end. Both of those are pretty good ways to express this area function. So the idea is now we have an expression for this area, and we are allowed to, change this right-hand boundary so that we can move it to the right or to the left and change things. So, all right, the next part says explain why geometrically a of 1 should be 0. And the idea here is if we put in 1 for x, it means that we're shifting this boundary all the way so that it's on top of 1. And the area there, if it's just a straight up skinny little strip, it's not even a rectangle. It's just a line segment. So the area should be 0. Yeah, it's just a vertical line segment at, at x equals 1, no area. Um, and yeah, if we were to plug in 1 into our formula, does it work out? We do 1 squared plus 1 equal minus 2, that equals 0. So that's working well with our formula so far. So I'm pretty happy about that. Now we have a function a of x. We're ready to consider how a of x changes with respect to x. Draw another vertical line on the graph directly above, t equals x plus delta x, where delta x is some positive number. So, gosh, I've already done this a bit here. Well, let's make a green line over here, and we're gonna represent this area, or sorry, this length as delta x. So the purple point, that's x, and then this green one is adding on delta x. Okay, so now we've drawn that. I think we're good. Let's go on to the next side. Evaluate the difference between the area evaluated at x plus delta x and the area at x, and simplify as much as possible. Hopefully the answer will involve both x and delta x. Okay, what geometrical meaning does this expression have in regards to the graph on the last page? So if we're taking this minus this, it'll be this bigger trapezoid where we go all the way out to the green line, minus the smaller trapezoid where we go out to, this yellow/pink line. That's really, the yellow-pink line should be the same. It's just one line. But yeah, I mean, it should just be the area. All right, let's do this. If we shade in that strip, this should be the area of x plus delta x minus the area at x. Because we're subtracting the big trapezoid and then we're subtracting the smaller one off of it. So we're just left with this thin strip of area. Okay, so that's the geometric meaning. Let's go ahead and see what we can do by plugging this in. If we start working with this, a of x plus delta x minus a of x. A of x plus delta x should be, oh, we don't want to do that again, sorry. We're going to plug in x plus delta x in for x squared. So x plus delta x squared. And then we're going to subtract off an x, right? Nope, we're going to add on the x. Okay, sorry. That's plus x. So plus x plus delta x. And then minus 2. Okay. And we're going to do the same thing, plugging in x. So we get minus this whole thing where we've got x squared plus 2x. No, not 2x, just 1. Just 1x minus 2. Okay. So that's this part. And then this is the other part. Okay. Um, cool. Let's simplify this down as much as we can. This becomes x squared plus 2 delta x plus delta x squared plus x plus delta x minus 2 minus x squared plus, nope, sorry, minus x plus 2. And then we're able to cancel a lot of stuff out. So when we're combining stuff, x squared is its own thing. So that x squared, oh, and minus x squared, those cancel out. Then we've got all of the, let's just do the x's. Oh, so those x's cancel out. And then this minus 2 cancels out with that plus 2. So those terms purely cancel out. And what we're left with is 2 delta x, oh, sorry, plus another delta x. So we've got 2 delta x plus another one. So that should be 3 delta x, and then plus delta x squared. Okay. Does that make sense? I think we're on point. That's looking okay. Um, cool. So let's keep going. If we that okay, pause. I feel like something's going wrong and I need to figure it out. That 3, I don't think should be there. Okay, I see what I did. Um, yeah, when I multiplied this out, I should be getting x delta x's, not just delta x's. So I need to fix this part. Um, yeah, we can do this in green. This should be 2x times delta x coming out of the outside and inside multiplication of those two. That makes a difference. Okay, now we can continue. So it's not 3 delta x. That was silly. It's 2x delta x. And then we've got another delta x. And we've got a delta x squared. That is looking better. Okay. Sorry for the mistakes. It's going to be fine. Now we're evaluating this limit. So we're going limit as delta x goes to 0. We've already figured out that top part. So I'm just going to throw in 2x delta x plus delta x plus delta x squared all over delta x. Thankfully, sorry, these all have a nice common factor. So we can go ahead and divide through by that. So if we divide through by delta x, we're going to get, oh, we're just going to get 2x for that first term. We're going to get a plus 1 for that next term, and then plus delta x for the last one. Because that was squared, it doesn't cancel out totally. And then as we take the limit as x or delta x goes to 0, this just turns into 2x plus 1. So what we just did is we are relating derivatives and integrals because I'm not sure that, I made it clear, but up here, we're doing integrals. We're trying to find area accumulated underneath this straight line. But what we're ending up doing here is taking the limit definition of the derivative. This is a difference quotient. It's a difference of y values over a difference in x values. And so we just took the derivative of an area function, which is a type of integral in itself. And so now we're kind of wondering, what object do we have after taking an integral, but then taking the derivative of that integral? And we've got this thing 2x plus 1. So uh, problem number 5, we accomplished. We took the derivative of an area function. And an area function is an integral. Um, we found the rate of change of area is another way, to say that. And then if we look at our solution here to number 5 and the original function and ask how are they related, okay, well, check this out. The function that we got here from number 5, that's 2x plus 1. And the one that we had originally was this function y equals 2t plus 1. How are they related? They're the same function with a change of variable. Let's go. Same function. Same function with a change of variable. Cool. Um, so based on what we've explored, can we describe the relationship between area functions and derivatives that we see? What we just kind of worked through is the fundamental theorem of calculus, part 1, where we have a continuous function f. That continuous function f is this original f of t equals 2t plus 1. Yeah, define the function big F being an antiderivative, right? So we're defining big F of x as this integral. So big F is an antiderivative of little f. But then when you take the derivative of big F, you get back little f of x. So you end up getting the same function back with a change of variable. Instead of being f of t on the inside of this integral, where one of the bounds is an x, this ends up being little f of x once you take the derivative of this area function. And this is really cool. This explains that area functions and derivatives can kind of undo each other. Fundamentally, if you look at it geometrically, the the rate at which this area is changing is the height of the function, where you're at. So yeah, the rate of change of area is the height of the function, which makes some sense, but it may be not completely obvious. I think this is a really good example of looking at the derivative as a rate of change, but instead of looking at the derivative as just the slope of a line, um, here we're understanding that the derivative is a rate of change, but when it's a rate of change of the area function, it ends up being the same thing as the height of the original function, which is, I don't know, super cool. All right, so that's fundamental theorem of calculus part one. Um, you could say, in some sense, um, integrals and derivatives are inverse operations. You know, and that's putting it simply, but I think that's what we saw here. When we take the derivative of an area function, we get the same function with a change of variable. So that's this one, and then I'm going to record the rest of the stuff on a separate video. So we'll see you over there. I need to do this, and then